In this lecture, we want to begin talking about hypothesis testing for population proportion. And now this hypothesis testing for proportion is going to be the same 5-step process, basically. So it's going to be the similar 5 steps, just different notation. So what I mean by different notation, so prior, the parameter we were investigating was mu, okay, the population mean. We were doing a hypothesis test for that. Now what we want to do, the parameter is P. We're going to do a hypothesis test for some population proportion. So there's going to be a lecture, 2 different ways to do this hypothesis testing. There's the critical value approach. That's what this lecture is on. And then there'll be a follow-up lecture that shows you how to use the p-value approach. All right, both are fine. Methods for hypothesis testing, obviously, as I've said prior, the p-value approach is more industry standard, how it's used in the real world, but this lecture will show you how to do the critical value approach. Okay, so here's the 5-step process, and I'm going to just do a high-level introduction here, and then I'm going to break down each step in the coming slides. So step 1, you're going to define the parameter. You're going to set up the test. So remember, in hypothesis testing, we have 3 tests: two-tailed, right-tailed, left-tailed test. Step 2, you're going to select the level of significance. That's alpha. Step 3, you're going to compute the test statistic. And notice here, it looks a little different. Okay, so first thing you're going to notice is z sub 0. Okay, so whenever you see the z, you know we're going to relate that to the standard normal curve. Okay, so that's good. And then I'll walk through all of these values in the coming slides. Then you're going to find the critical value or values in critical region or regions. And I'm going to give you a nice cheat sheet for this to help you on that. So that this should be pretty straightforward. And then step 5 is you're going to be your conclusion. So remember, you can either reject or you can fail to reject them. Okay, so let me go through the steps in a little bit of detail. Okay, so step 1, you're going to define the parameter. Okay, the first thing you're going to do is it's going to be let p equal to, and then whatever proportion you're investigating. Okay, and then we have to set up the test. Okay, and so we're going to either be a two-tailed test, and remember the keywords for this. This is like, I think the proportion has changed or it's different. We'll set up a left-tailed test. Okay, and what you're going to be looking to show is no way the proportion has decreased or gone down over time. And then we'll set up a right-tailed test. Okay, where we're investigating to see if the proportion has increased or gone up. Okay, so note that the null hypothesis in all cases is a statement of equality. Okay, we're always going to have p is equal to some number, and then you're going to use the keywords to figure out what the alternative is. Step 2, you're going to get your level of significance. Okay, this is alpha, and we're only going to do the 3 different levels here: 1%, 5%, or 10% level of significance. Okay, and I'm going to give you a cheat sheet to help you find what I have next here, or in step 4, the critical values or critical regions. All right, but this will always be given in the problem, so you just have to find this out or pull it out in the problem. Okay, then you're going to have to compute the test statistic. And it's z naught is equal to p hat. Well, we know that that's just x divided by n. That's the sample proportion. P sub 0, we'll look back here. Look where it comes from. It comes from the null. It's the assumed value of the population proportion. And then, so it's p hat minus p sub 0 divided by, and then the square root of p naught, or p sub 0, times 1 minus p sub 0 divided by n, and we know n is the sample size. All right, so we're going to work this problem in our calculator a bit today. So we'll get a chance to compute 3 test statistics so you can see how it's done. Okay, step 4 is the critical value or critical regions. Now, if you have a two-tailed, right-tailed, or left-tailed test, two-tailed has 2 critical regions, and you can see I have the critical values associated to them. So these are the critical values. And then you're going to shade everything to the left and everything to the right. Okay, and those are the critical regions. Right-tailed test, you can see here, has 1 critical value, and then you're only going to shade the area to the the right of it. And then you have a left-tailed test, okay? Well, here are the critical values for the left-tailed test. You're going to shade everything to the left. And when your test statistic falls in one of these critical regions, you reject the null hypothesis. Right? That's why we find this. So I gave that away a little bit here. Step 5 is our conclusion. If the test statistic is in the critical region, all right, one of these shaded regions here, okay, we reject the null hypothesis. What this means is evidence supports the alternative. And if the test statistic is not in the critical region, what happens is we fail to reject the null hypothesis, meaning evidence does not support the alternative. All right, let's just do 3 examples of this so you can see how this process of hypothesis testing for proportion is done. Okay, so a little bit old data here. So according to a 2010 Department of Education report, 30% of adults aged 25 years or older had a bachelor's degree or higher. So a researcher, a little bit of a typo there, researcher wants to conduct a test to see if the proportion of individuals who have a bachelor's degree or higher has increased. So I highlighted that here. That keyword tells me it's going to be a right-tail test. To conduct the test, the researcher samples 1,000 adults. So look, you're given 1,000 adults, age 25 years or older, and finds that now, X, 320 of them have a bachelor's degree or higher. So what that means is you can actually find p hat, sample proportion. So it's 320 over 1,000, and it's 0.32. So at the 0.05 level of significance, so you're given alpha, is there sufficient evidence to suggest the proportion has increased? Okay, so this is all the information you need to figure this out. So note that in 2010 it was 30%, and what we want to see is that it's increased since then. All right, so let's go through the steps. Step 1, let's define the parameter. Okay, so this is going to be, we're going to let P be equal to the proportion of adults 25 or older who have a bachelor's degree or higher now in the current year. Okay, now in the current year, because we know what it was in 2010. I'm going to go back for a second. We know what it was in 2010. It was 30%. And we want to say, no, wait, it's increased. It's gone up. So now we have to set up the test. So we said, because of the keyword increased, is that it's a right-tail test. Okay. So what we're going to assume, our null hypothesis is going to be no change, so that it's going to be, we'll assume that it's still 30%, and what we're looking to show evidence for is, wait a second, no way, it's gone up, it's greater than that. Level of significance is alpha 0.05. So now we just got to compute our test statistic, okay? So p hat, I found on the previous slide, it's 0.32 minus p sub 0, 0.30, divided by square root of p naught, right, come from the null, 0.30 times 1 minus 0.30 divided by the 1,000 people in this sample. All right, it's a little bit tricky, so everybody, watching, it's definitely worth it to follow along with your graphing calculator as I do these problems, okay? So the numerator, we got to put in parentheses, 0.32 minus 0.30, close the parentheses, divide square root 0.30 times another set of parentheses, 1 minus 0.30, close that set of parentheses, divided by 1,000. Now, if you have a TI-83, this is important if you have a TI-83, it did parentheses, square root a set of parentheses, you need to have a second set of parentheses to close it. But we should get this, okay? It's 1.380. All right, so let's find the critical values, critical regions. So it's a right-tailed test. Okay, what that means is you're going to draw a normal curve, standard normal curve, centered at 0, and you have one critical value out here. Well, right-tailed test alpha is 0.05, so you're just going to go back, right-tailed test alpha is 0.05, so it's 1.645, 1.645. And you're going to shade everything to the right. Okay, so this red shaded area is my critical region. And this is my critical value. So what you do is you look at your test statistic. It falls between 0 and 1.645. It's like right here. Okay, notice how it does not go past the critical value, so it's not in the critical region. So what's going on here is we fail to reject the null. This is because our test statistic is not in the critical region. So what this means is that evidence does not suggest the proportion is increased. For whatever reason, since 2010, this evidence that we've collected suggests that the proportion of people aged 25 years or older who have a bachelor's degree or higher, it hasn't gone up. It hasn't increased from the 2010 level. All right, let's do another one. So in a national poll of 1,000, so look what you're given. You're given n is equal to 1053. Okay. We're asked, do you support passage of an economic stimulus bill that includes support for state budgets? So there was just this poll for whatever reason, and Congress wants to pass this stimulus bill, and they want to know if people support, okay, a provision that includes support for state budgets. All right, so of that, 548 said, yeah, sure. So P hat is 548 over 0.53. So it's 0.52, so I'm just going to round it off. So then again, at the alpha is equal to 0.05 level of significance, does the data provide sufficient evidence to conclude that a majority, so this is weird, of U.S. adults support passing? So what's a majority? What represents a majority? Being greater than 50%. Okay, so I want to test to see if it's greater than 50%. So greater than 50%, that sounds like a right-tailed test. Sounds like a right-tailed test again. So we got two right-tailed tests in a row. Okay, so we're interested in the proportion of people who support passage of this bill that includes support for state budgets. So that's our parameter. Proportion of adults who support passage of bill with support for state budgets. So now that we've defined the parameter, we're going to set up the test. So we wanted to test, just looking back, that a majority. So we wanted to show evidence that it's greater than 50%. So when I set up my null and alternative hypothesis here, so I want to show evidence that it's greater than 50%. So that's what I'm looking to show evidence for. So if we're going to look to show evidence that it's greater than 50%, we'll start with the assumption that it is 50%. right? Because we know that if we want to show evidence that it's greater than 50, these two numbers have to be the same value. Like if you look back, even in our first problem, they're the same numbers, 30%. So here it's going to be 50% in both. So we select the level of significance. Again, it's 0.05. And now we're going to compute the test statistic. So our p hat here, I rounded off to be 0.52 minus p naught, which is 0.50, comes from the null, divided by the square root of p naught times 1 minus p naught, divided by, and our sample size again was 1053. So we're going to grab our trusty calculator. And remember, put all this in parentheses. So it's 0.52 minus 0.50, close the parentheses, divide, square root, 0.50 times, and then in parentheses 1 minus 0.50, divided by 1053. And remember, if you have a TI-83, you have to close this set of parentheses. And you should get 1.298 when I round it, 1.298. Okay, so again, next we're going to find the critical value, critical region. So it's a right-tailed test. So there's one critical value, and we're going to shade to the right. So looking back, here's what you do. Alpha, 0.05. Right-tailed test, alpha is 0.05. Critical value, again, same as last test, is 1.645. So again, you'll see this one is also the same conclusion. Our test statistic does not fall in the critical region. It's over here somewhere. It's between 0 and 1.645. So here we failed to reject the null. Because our test statistic is not in the critical region. So even though the sample mean, or the sample mean, excuse me, sample proportion came back at 0.52, like that's just one snapshot in time. It's like one poll. So it just doesn't provide enough evidence to say for sure a majority support the passage. So evidence does not suggest a majority does support the passage of the bill. I always like to do this problem because, you know, whenever you see a poll or something that's like, oh, 52% of Americans believe this, you know, got to be sure what that's really saying. Like, that's why we talk about, okay, confidence intervals. Well, you know, if that's just one statistic, what does the real value be? And then look, you can even do a hypothesis test here to show that it doesn't even indicate that you can say for sure there's a majority. All right, let's just do one last one here. So a researcher, a little bit of a typo again, a researcher claims that 10% of the US population is left-handed. Okay, so he or she, this researcher is saying 10% are left-handed. That's it. So here's what you're going to do. We want to test this claim. Let's test to see if the researcher is correct. So this is what we're given. We're given the sample size of 750 people. And it was found that X, 92 of them were left-handed. Okay, so let's see what our p hat is from this. 92 over 750. So and you get 0.1223. I'll round it to 3 decimal places. Okay, so does the data support the claim by the researcher? And again, use the alpha is equal to 0.05. Okay, so notice this one's a little weird because there's no like keyword here that says like, oh, it's gone up, it's gone down. So here's what's going on. The researcher is saying it's 10%. Okay, so the only way the researcher could be wrong is that it's not 10%. Well, if it's not 10%, that sounds like a not equal to. So this is going to be a two-tailed test. Okay, so let's go through the five-step process. Define the parameter. Well, if you look back here, we're investigating the proportion of the US population that is left-handed. So let P equal proportion of population that is left-handed. And so when you go to set up the test now, it's going to be a two-tailed test. Okay? And here's what's going on. The researcher's claiming it's 10%. It is equal to 10%. Right? So then what we're going to look to show evidence for is it's not equal to 10%, that the researcher's wrong. So the null hypothesis here is the researcher's right. And the alternative here is the researcher's incorrect. All right, so again, level of significance was given to be 0.05. Compute the test statistic. So my p hat was 0.123 minus p naught, comes from the null, 0.10, square root of 0.10 times 1 minus 0.10 divided by the 750 people. So let's go through our calculator here. So this is the tricky part, right? It's always the denominator, plugging this in. But if you do this correctly, you should get this, 2.099, or basically really it's 2.100 when you round it off, okay? Because the 6 would make that a 10 and so on. It would cascade. So 2.100. Okay, so next, it's a two-tailed test. So when we go to find the critical region, find critical values, critical regions, and critical values. You're centered at 0. And there's one critical value up here, and you're going to shade to the right. And there's another critical value down here, and you're going to shade to the left. So let's see, two-tailed test. So two-tailed test, you're going to look here. Alpha is 0.05, so the critical values are 1.960 and negative 1.96. So you have negative 1.960 and you have 1.96. Well, look at my test statistic. It's just past it. It's like right here. It's in the critical region. Okay, so it's past this 1.960. It goes past it. So what do? We reject the null. Because test statistic is in critical region. And what does this suggest? And it's basically saying evidence supports the alternative. And its evidence suggests the researcher is incorrect. All right. I'll follow this lecture up with a lecture on the p-value so you can see another way to hypothesis testing for proportions.